My typical plan with these secret Endscreen videos is to keep them unlisted, but this one, which is associated with the video about topology and the inscribed rectangle problem, I'm a little bit late in making, basically because for that video I was running right up against a deadline of my own holiday break. I'm making this one public just to give those audience members who are most likely to click on it, those early viewers of the video, a chance to actually see. A nice category of discussion point with these videos, which I think of as a kind of office hours, is to talk about all of the interesting things that come up in making the video that don't really show up with the video itself. Because of course, it's a lesson about math in some way, and so I'm talking about some piece of math. But often there's a lot of other interesting mathematical puzzles and coding challenges that come up in the effort of actually animating it that I usually don't have an outlet to talk about. As an example, one of the central ideas in that video was about this association between pairs of points on a loop and individual points on a Möbius strip. And it could be any loop. Here I was using kind of a gingerbread shape because it's the holidays, so why not? And at various points, I would maybe want to have some animation like this one, where you're generically wandering through pairs of points and looking at some wandering point on the strip. And I could cheat. I could just kind of make this up by having like a random point on that strip and a random pair of points over here. But it's very intellectually satisfying for it to be the true association, the one that's continuous in both directions and all that. Because, for example, otherwise, I'm sure that some eagle-eyed viewers would notice, whenever you have the 2 points collide into one, it's important that the point bounces off the edge of the strip. That was very important for the discussion. And the challenge here in rendering it, it's not that much of a challenge, it's not that hard, but it was an interesting puzzle that came up, is to explicitly describe what that association is. And here's what I mean. Each one of those points on this loop, you can think of as a number between 0 and 1. So this gingerbread loop is parametrized as you walk around it. That dot is going to be associated with some number between 0 and 1. So we have a pair of numbers between 0 and 1, and we want to find some specific point on the Möbius strip. Now, the way that the Möbius strip is rendered, though, is going to be some explicit parametrization. So for context, there's going to be some general function to render surfaces if you give them u and v parameters. Often I like to think of both of them as ranging from 0 to 1. So the function used for the Möbius strip that's going to take in u and v and spit out some point in three-dimensional space takes in these two values, each between 0 and 1. Basically, I first rescale that v so that I'm going to think of it as an angle between 0 and 2 pi. Whenever I code, I kind of like to write 2 pi as tau just to giggle to myself. That one is basically going to describe as you're walking around the loop. So what's the angle as you kind of go all the way around? And then this other parameter is going to be something that you want to rotate 180 degrees as you're walking around that loop. So it'll start out pointing in one direction, and then as you walk around, halfway around it should be 90 degrees up, and then another halfway around it should be pointed the opposite way. Then after that, just writing out what the explicit vectors are, kind of adding them based on some configuration for the relevant size. And the challenge here is that this, which is an association between a pair of numbers between 0 and 1 and an individual point on the Möbius strip, is not the same thing as the association that we want to describe from the video, where you have a pair of points on the loop, some pair of parameters landing on the strip. For example, it's ordered. If you swap the values for u and v, you would get a different point on the Möbius strip. Whereas the whole point here is if you swap the points on the loop, it shouldn't be different. Also, you can tell that the edge doesn't correspond to pairs that are the same, because if you plug in some pair of values like 0.5, 0.5, it's not necessarily going to land you on the edge. So the challenge, again, it's not that hard a challenge, but it's like a fun little puzzle to think about, is if you're parametrizing the Möbius strip like this, then how is it that you explicitly describe this relationship? And I'll show you another place where this came up, which was an animation. It never made it into the final video, actually, but it was fun to make. So if you'll remember, we first constructed this association between ordered pairs of points and the torus, which basically came from taking the unit square of parameters and kind of gluing the left edge to the right edge and the bottom to the top. And then to describe unordered pairs, we folded this unit square along the diagonal and then deduced why that had to look like a Möbius strip. So the thing I wanted to show that I thought could be fun was, what does it look like if we do that folding not in the space of this unit square, but we literally fold the torus into the Möbius strip. So for example, if I draw this red line along the diagonal, which is all of the pairs of points that look like x comma x that look the same, then on the torus, it looks like this red line that goes around in one direction while it's also going around the handle direction. And then I want to turn this torus into the Möbius strip in such a way that the coordinates described by u comma v and the ones described by v comma u each land on the same thing. This is essentially just animating what the solution to the puzzle I mentioned a moment ago was. And the way that it looks, we'll go ahead and let it play out here. The way that it looks is this. which is kind of fun. I made this, I added some narration in there to include in the video, and then I realized it's not actually all that clarifying. It's not really relevant to the storyline. This is just me having a little too much fun with the animation. Not great for the main video, but perfect fodder for a secret end screen video. So there you go. Another little coding puzzle that came up here was in explicitly showing the inscribed squares and the inscribed rectangles. For example, here I'll pull up a copy of the opening scene, kind of describing closed loops, inscribed squares, and all of that. And what I wanted throughout the video was something where I'd have a generic function that takes any loop, and then I say, find me a rectangle somewhere in there with a specific aspect ratio, like find me a square, for example. And so that way I could have, animations that would find various ones. And in particular, I wanted one where as you're transitioning between two different curves, at each point along the way, it finds a square. Now you'll notice though, I did one that kind of works, but it doesn't actually work very well. Like on this transition, there's a lot of points where it's definitively not a square that it finds in there. And again, this was one of those things where I was kind of running up against a personal deadline, could have coded it better in some way, but what I wrote worked well enough for my purposes. And the way that I was thinking about this, and I'm quite sure that I could do it better now, but if you're curious, the way that I was thinking about this was to kind of use the method described in the video. If you remember, the main point in that video was if you're looking for 4 points that make a rectangle, you can think of it as finding 2 distinct pairs of points so that they have the same midpoint and the distance between those is the same. And then if you further want to find something like a square or a rectangle with a particular aspect ratio, you could maybe consider the angle between them. So what I would do is I would search through the various quadruplets of points on the loop and then assign a cost to it associated with how far away are the midpoints for these diagonal pairs and how different are the distances. And then also how much does that angle deviate from what I want. And then I think it was just like a gradient descent procedure or something like that. When I tried this out, it took a little bit of tweaking. For the most part, it worked well enough. If I asked for it to find a square, it would find a square. If I asked for it to find a rectangle of a particular aspect ratio, it would do that. And this came up later when I wanted to describe the green lob theorem, saying that we can find rectangles of every possible aspect ratio. But like I said, it didn't work perfectly. And I actually, I rendered this certain animation, but I cut it out from the intro scene just because enough of them weren't actual squares. So if you look at the original video in that intro scene, rather than doing this transition between them, I kind of just flash at the start and the end when there's an actual square. So I'm curious, in comments for the coders among you, how would you approach this? You want to explicitly find squares, explicitly find rectangles. Preferably you want it to be computationally efficient in some way. What strategy would you use? And more broadly, I think this highlights kind of a fun thing about topology, or at least a noteworthy thing about topology, where it's very non-constructive. It'll show you things must exist, but it doesn't tell you anything about how to find them. And nowhere do you more viscerally feel this disconnect between proof of existence and explicitly finding the existence than if you're animating a video about it. We've got this conclusion saying there must be a rectangle. We've proven there must be a rectangle. But then the task of actually coding it up requires you to think about it in a completely different way. And that kind of pattern comes up a couple different times in making videos where the act of animating it requires thinking about it in a very different way than what I'm describing in the video. Usually there's not an outlet. That's what makes these fun. For future secret end screen videos, I'm going to try to be more consistent about having something there when I publish it. The next video in particular is going to be a very fun one on the channel. It includes a very special guest and a number of animations that are well outside the usual wheelhouse of the sorts of things I describe. So it'll be different. I think you'll like it a lot. It'll be fun. And I'll see you there.